Hi, we're the Washington College Electric Boat Team, and this is our final presentation to the American Society of Naval Engineers for 2025 Promoting Electric Propulsion Collegiate Competition. My name is Taba Jamil.
I'm Tyler Little.
My name is Thomas Lizaralde.
I'm Cole Davis.
I'm Douglas Hughes.
I'm Max Sansbury.
My name is David Audette.
With changes in the competition rules, our initial thought this year was to reuse one of our previous boats. This would have been the easiest route to go. However, we didn't think this would give us the best results. Both our trimaran and monohull were built to carry the weight and withstand the forces of more powerful high-voltage systems. Although they could be adapted to 55 volts, they would be overkill, forcing us to carry a lot of additional weight and reducing our top speed. We also wanted to carry our new boat inside a 7x12 cargo trailer, which led us to look for something of a smaller size.
This year's hull started as a partially built wooden Ben-Hur 11 hydroplane, and after we purchased a partially built hull, we wrapped the underside with a single layer of 9-ounce cloth and added 3 layers of 9-ounce cloth on the deck, making it strong and allowing it to support our weight.
We built a watertight compartment that houses the battery, motor, controller, and the forced air and water cooling components. We also filled the sponsons with 2-part expanding foam, which made the planing surfaces more rigid and added flotation. Further, we cut a slot for our shaft at the center of the hull to allow a drive shaft to pass through and spin a prop directly. We used Cusa composite material to reinforce the floor and other structural parts of the hull that were affected by our adaptation and drivetrain.
Being aware of the hull type and how it would react to different conditions on the water, we designed and installed a windshield that will help deflect spray and keep the cockpit dry. Since we know the crossing of the wake of competitors with each lap and perhaps dealing with the wind-driven fetch across the racecourse.
We are using a Mont Energy motor. The ME1616 produces 45 Newton meters of torque with an approximate kV rating of 75, meaning it will spin 3600 RPM at 48 volts.
With our custom 15S 54-volt nominal battery, the unloaded motor will spin at 4050 RPM. With a typical outboard lower unit using a 2-to-1 gear ratio, we knew our ME1616 motor would not be as ideal in an outboard conversion at this lower voltage.
Therefore, we decided to modify the hull and run a straight shaft between the motor through the hull and directly to a propeller that would work well with the real world, loaded RPMs around 3800 to 3900 RPMs.
We used all this data to help us select a propeller that would be the most ideal for this application. We also selected a cleaver-style racing propeller. Although this style prop is generally less efficient, it is better equipped on a hydroplane to handle the potential cavitation as the boat is skimming along the surface of the water. We found a used 10-inch diameter, 15-inch pitch, 3-blade cupped prop, which was ideal in every way except it was designed for mounting on a 14-spline shaft of an outboard motor lower unit. To utilize the 1-inch stainless shaft we already found in a salvage yard, we had help from the college's research boat captain who TIG welded the 14-spline shaft onto the end of our 1-inch solid stainless shaft.
The motor itself is controlled and fed AC power by a Curtis motor controller. For throttle control, a wig-wag style throttle which uses 2 potentiometers to provide separate signals for forward and reverse.
Since we are no longer using a modified outboard motor in our drivetrain, we needed to add a rudder and steering wheel to control thrust direction and steer the boat. So we decided to use a modified fiberglass rudder from a Nacra sailing catamaran, which is controlled by 2 braided stainless aircraft cables that run down either side of the hull. These cables are wrapped around a custom 3D printed steering hub with a small steering wheel mounted behind it. We decided to use this lower tech pull-pull cable-driven steering mechanism instead of the push-pull cable-driven method we previously used because it is more compact and lighter in weight.
In our first year competing at PEP, we were using a 16S lithium iron phosphate system, which pulled about 105 amps on average, producing about 5.5 kilowatts of power. Looking back at this previous 48-volt system, we considered using a similar battery architecture this year, but there were some factors that concerned us.
Firstly, the 280 amp hour cells could provide the current we needed, but at 14.3 kilowatt hours, it's about 3.5 times the capacity we calculated we would need to run the 5-mile race. Since prismatic lithium iron phosphate cells are generally rated at about 1C continuous discharge, most smaller cells that had the capacity we desired would not be able to sustain the current we needed. Also, we considered using some specialty lithium iron phosphate cells that were able to sustain a higher C rating, but they still didn't compare to the performance we would get from a battery that had a nickel manganese cobalt lithium ion chemistry.
Moreover, due to the very limited space, specific arrangement choices, and battery style, we ultimately chose to use the Molicel P'25 cells. Those are able to produce 45 amps continuously with a 4,500 mAh capacity. We decided to build an atypical 15S battery configuration to best take advantage of the 55 volts nominal voltage limit. With these 3.6 volt nominal cells in a 15S configuration, the resulting battery is 54 volts nominal.
In arranging and spot welding our cells together, we chose to maintain an air gap between the cells to decrease the risk of overheating and maximize cooling without adding any extra weight, with only minor additional space needed.
We had issues with our original idea of the battery stack when we realized we could end up short-circuiting cells in the 3-tier stack if one layer came into contact with another layer near it. We also could not use anything in between the 3 layers to insulate cells from one another. However, the challenge came from creating an insulator that would also let cooling air pass easily through the stack of cells to dissipate heat.
Our second problem arose when we connected one 48P cell cluster to the next. With 16 by 3 cell layout on each cell cluster, the full current would be carried across 16 thin nickel strips, in each case of the series connections between each of the 15 clusters. Since we were planning to pull 250 amps continuously during the race, this would require over 15 amps across of the 16 nickel strips, nearly twice what they are rated for. This pinch point in our electrical system would limit a current and, as a byproduct, would produce significant excess heat, essentially limiting our power while making cooling all that much harder to accomplish.
We fixed this by redesigning the battery architecture once again as a single flat array of 720 cells with 48 in parallel and 15 in series. This single layer layout would be easier to cool since no cells would be sandwiched in the middle of a multi-layer stack anymore. The only downside is that this requires the battery tray to extend forward over the motor compartment, where water intrusion through the cutlass bearing is a real possibility and somewhat expected.
Additionally, we designed the system to use a high current contactor to join the 2 halves into a 54 volt nominal battery at a flip of the switch. But we also would be able to provide safety of a maximum of 28.8 volt nominal if the kill switch is pulled or the system is turned off.
Lastly, we are aware of the increased risk of the battery chemistry and designed redundant monitoring systems for battery temperatures. We would rather have a redundant system in case of failure than realize we have a cooling problem sometime during the race.
9 powerful fans will circulate air through the cells within the enclosed compartment, so we have 2 additional ducted fans that draw air into the compartment and exhaust the heated air out the back.
We have 8 students and our advisor coming to PEP in April. We're looking forward to seeing all the teams and their boats in Virginia Beach. As always, we want to thank the American Society of Naval Engineers for organizing this valuable and engaging hands-on experience and for providing much of the funding required to make it all happen.